soon with the second part, so I don't think that there will be a third part, but let's focus on the second one. So I already show you that the goal of formal method is building applications that are correct. And now in this part, I don't know the number, but I will focus on a formal verification, which is we can think about it as a kind of sub-branch of formal methods that aim at proving application correct. So before it was about building applications that are correct with respect to differential privacy. Now we take something that people can design in their own way, and we try to prove them differentially private, yes. So formal verification is quite old. It started more or less when computers started, and I like usually present it through the word of Turing, who already thought a bit about this problem, and he was asking himself, how can one check a routine in the sense of making sure that it is right? And the answer was already there. It is in order that the man who checks, okay, his mistake was this one, not only a man, but a man and a machine who checks may not have too difficult a task. The programmer should make a number of definite assertions which can be checked individually, and from which the correctness of the whole program directly follow. And this is what I will do in this hour. I will take some example and do exactly this. Go step by step through assertions and show you how we can prove a program differentially private, if I get there.
Amazing how they had color pictures.
Okay, I could have taken a real picture, right? So mainly the overall picture is this, we provide the program with some annotation, and the verification tool try to check if this is a valid program, so that satisfy the property we want. In particular for us it will be differential privacy. An important aspect of modern verification is that we use a lot of tools which help us doing this in as automated as possible. Okay. So let's look back at our example that we started with, this one. So we already saw that this failed to meet the specification. It was the example about addition. Now let's try to fix the program first. I just replace 0 with x. So now I'm pretty confident that this program computes addition. And so it meets the specification. Now, how can we prove that it meets the specification? If you have already seen this, maybe it's not anything really new, but a standard way to do this is to try to push through assertion this precondition forward and try to derive the postcondition from it, going through the program. Another approach would be to pull the postcondition backward, so trying to see if this indeed follow from that. Okay. Now, this is a kind of game. I will choose the direction of going forward because I think it's a little more easy to present on paper, although automated technique try to go more backward, but I will try to use the forward direction. And I call it a game because I will introduce some rule of the game, which tell us how to step from a pre-formula to a post-formula by looking at each of these. So every time, later I will do several steps at the same time, but every time I pass through one of these lines, I will apply a rule of the game. Now, I will use only rules that are correct, that they are sound, and I will avoid doing this here, but they are proved correct, again, with respect to some semantic model, as I was saying before. I will not do it here, but there is the rule that when I introduce a new rule, I need to do this proof. I did it before. I will not do it here, but this is important.
But these are these human proofs, or is there like another turtle under this? When you say needs to be proven correct, like by you or by like another machine?
You can do either. You can. Usually we do it on paper. We do a combination, so you can prove it with another machine. Okay. Yeah. So yeah, they are still now. Mainly, if we think about trust, the trust has been moved to this, the soundness of this rule. So these are the trusted components. Okay. So let's try to prove correct this program. Now I reformulate a bit what I call the precondition. I just introduce and the postcondition, I introduce two variables, V and W, which make it a little easier, but if you do a little of rewriting, the precondition is the same. And I will start by pushing this condition, so it's exactly the same condition. I just remove the precondition name through the function. And we are just putting it in the function, so I assume that this is a simple rule that I can apply. I just push it there. Now, the question is, how shall I move next? So what is the first rule that I introduce? Here we have an assignment that say R is equal to X. So what shall I do now? Now, what we can do is, using this rule, let's say that if we have an assignment like this, where to X we assign E, then we can derive, starting from a formula where every occurrence of X is replaced by E, the formula itself. Let me show you some example that maybe it clarifies what I mean. So for instance, I can prove from A is equal to Y, I can push it forward and say that X is equal to Y, because X inherits the property of A. Another example, I can, from X plus 1 greater than 0, I can say, if I do X equal to X plus 1, that X is greater than 0. Because again, I inherit the property of X plus 1. Yeah. Another kind of example is from 3 equal to 3, applying the fact that X is equal to 3, I can derive X is equal to 3.
So you're allowed to replace every occurrence of 3 you want? Or because otherwise you would get X equals X.
No, notice how I formulate it. So the formula, this is the only place where I go a little backward. So the formula is the one on the bottom, and I replace in the top. So I replace all the occurrences. For instance, here...
All the occurrences of 3 with X would get X equals X as your new formula. You chose to replace 1.
Yeah, I replace X with 3.
So shouldn't the precondition be X equals X instead of 3 equals 3?
No. I can. Also, that is good. But this is good as well.
So you're free to choose whichever.
Yeah, exactly. That's where a bit of creativity is needed. So that's where you can choose. So you see here I replace again this X with X plus 1. I replace this X with A. So going down, I have some choice. Okay, so if I apply this rule here, mainly what I get is that doing some transformation, now I have R equal to V. I can apply this rule again, and I also get that N is equal to W. And here is where I use this additional variable. Now, let me change another rule that I can do, that I didn't write up explicitly, is that I have a bit of game in how I can change this formula if I preserve the validity of the formula. So in particular here, I rewrite R equal to V plus W minus N. So why I'm allowed to do that? Because N and W are equal, so I'm adding and removing the same element. Okay? All right. So why do I need this at an high level is because now I'm going into a while where I need some form of invariant to be preserved. And this is the reason why I do this, and we will see in a moment when I give the rule for while. Actually, let me remove, I change it a little more because I now say something like this. R plus 1 is equal to V plus W and minus 1. Again, I'm adding plus 1 on both sides, so the equality is preserved, and I forget a bit the rest to make a bit simpler. Now I try to propagate it through the while, and I keep applying the rule we saw before, and this gets transformed. In particular, notice that now I replace this R plus 1 with R, and then I replace the N minus 1 with N. Now, if you notice, here I have the same rule, the same constraint I had before entering the while. I don't know if I emphasized this enough, so let's go back here. So I had this constraint, R equal to V plus W minus N. So what I show with this step is that this can be recreated after going through the while. Now, this brings us to the while rule, which is this one. If we can find a formula that, if we can find a formula for which we can do this, so we can take the formula and the condition of the while and prove the same formula after the body, then I can prove that this formula is also true for the while. It also holds for the while, and in particular, it will hold with the negation of the condition after the while. Yes?
Does that show that the condition is ever violated? Like there's a termination issue on the while loop?
Yeah, there is some termination issue that I'm completely leaving under the carpet here.
Right, like in particular, if y was negative, the problem with y being negative was not sort of exactly correctness of the formulas, it was that the program would run forever.
Yeah, exactly. So usually there is, we distinguish between total correctness and partial correctness, whether you also prove termination or you assume termination. There are techniques to deal with all of this. I just try to leave them under the carpet to avoid the discussion, but I'm happy to discuss if you're more interested. Yeah, but there is that issue. Yeah. So in general, we call this kind of formula an invariant because it's an invariant through the loop, and it allows us to prove that the formula still holds after the loop with the negation of the postcondition. So in particular, if I do this, I use this rule, and the same formula will apply here, but also with the negation of the condition. So the formula is this, and I apply the negation of the condition, which say that mainly n is equal to 0, and so this will become just R equal V plus W. And this is actually what we need for matching the postcondition. Okay, so this is a high-level introduction to how verification works. Now, I did it manually, but let's try to do it with a tool. Let me see if I can. I just want to give you a feeling of how far we can go. 1 second, otherwise, all right. Oops. All right, my slide is designed very badly. All right, so now then I want to say also, maybe I need to connect. In the meantime that is connecting, I wanted also to correct something I said before. Pink actually already in the first version contained the exponential mechanism. I said something wrong before, so it's available, it's here. And yeah, it was there. All right, so this, I don't know if you can see it, but is something, let me correct this exactly how we did it before. So this is exactly the example we were looking at, where requires is the precondition and ensure is the postcondition. And we also provide an invariant to the program. Now, if I try, this is a tool that people at Microsoft Research design for this kind of verification. Now, if I try to execute the original program, we have some error. We cannot prove it correct, and we know that is not correct because it doesn't compute the addition because of this 0. So if now I fix it to x, the verification goes through and it says verified. Okay, so this is to give you a bit of a flavor of how much of this is automated. In particular, you see what we need to provide is this part and this part. Now, there is a lot of research into try to remove this part at all. So inferring invariant is a very active research topic, and I think also this tool does some inference of invariant. So ideally, we would like really to provide just precondition and postcondition, and all the rest be done automatically. Okay? All right.
But finding the invariant is probably the hardest part in the...
Yeah, finding the invariant is the hardest part, and people are considering many different techniques to do that, from constraint solving, quite advanced constraint solving, to using machine learning technique. But I think especially in the constraint solving, they have a very sophisticated technique to find the invariant. Assuming that the precondition and postcondition are correct, they find the invariant. Yes?
Like if you're verifying more complicated programs, like how easy is it to specify things like the postcondition? Like if I wanted to, like your example of a postcondition is something that's basically like a first order operation, which is
exactly. So let's look at one more complex postcondition.
Something like a little non-trivial, like sortedness, like how, I mean.
Is this trivial?
No, I'm saying like this sounds very non-trivial. I'm saying
okay.
Like, you know, where between like x plus y and like this program is differentially private, does this start to become kind of challenging?
Yeah, so I think let's take a sortedness, which is something that people have looked a lot into. So specifying the postcondition is quite easy because you need to specify of course there is some kind of mathematical way of specifying. Actually here, in this tool, you can use the same language to specify both the program and the postcondition. And you can specify a predicate that say this list is sorted, which doesn't have to do at all with the algorithm that do the sorting. And then usually is really just about finding the right invariant. That's it.
So in writing such a predicate, you're allowed to use quantifiers?
You are allowed to use quantifier, yeah. I will come back to this a bit later when I will talk about solving. So let's talk about differential privacy. And let me take a simple example. This is slightly different from the one I took before. This is just compute. I try to take the simplest one, just computing CDF and then adding Laplace to this. CDF of one value. So just how many elements of the data set are less than C. Okay? So now the question is, what are precondition and postcondition here? So ideally, by the definition, we know that we would like something like this. For every two databases differing in one individual, the precondition. And then the result are epsilon delta indistinguishable. Okay? So, yeah, this is what ideally we would like. Now, there are two problems here. So the first problem has to do with the precondition, with actually both of them, is this quantification of two databases. I already mentioned this before. So who are these two databases? If you look at the verification we did before, we were working with the input. But here we are talking about two input. Okay? The second one is this one. How we formulate the result are epsilon delta indistinguishable. Okay. So to solve the first approach, there is a classic technique in verification, which is consider relational reasoning, where we consider, instead of one program, we consider two programs. In particular, now we can talk about the input of one and the input of the other. Here I took the same program because we are interested in verifying differential privacy, which usually talk about one program. But in general, and for verification, it's convenient to have two programs. Although I will use only one program in my presentation. Now, the problem is the postcondition. So now we can express the precondition. The problem is the postcondition, because this is what epsilon delta indistinguishability means. Now, why this is a problem? The problem has to do with the whole verification infrastructure. So I say that we want to rely as much as possible on automated and semi-automated tool, as you saw in the simple demo I gave. We have behind the tool that solve constraint. Now, do we have some good decision or semi-decision procedure for epsilon indistinguishability? And is it the way to go? So, just if you are not too familiar with solver, or maybe you are more familiar than me with some kind of solver, let me try to give you an idea of how we think about solver in programming languages. So I'm sure you all know how to solve a linear set of constraints. I think is something that most of you have seen before. And these usually we can consider them as kind of easy because they are simple constraints. This doesn't mean that it's always good having many of them. We know that there is complexity issue, but here I'm not considering complexity issues. But I'm trying to motivate the kind of solver we use. So these are, in my view, quite simple. Then we have nonlinear set of constraints, which start to be more complex. And then we have first-order formulas with quantifiers. And these are all also quite complex, depending if you are over the real, if you are over the integer, if you are over a mixed integer and real. And then finally, there is what we use, which are satisfiability modulo theories, SMT solvers, which put together different theories using first-order logic. Okay, so in this kind of setting, we can specify predicates. We can have numeric, for instance, nonlinear arithmetic, and we can have a linear arithmetic. We can have a bunch of different theories put together. Okay? This is the kind of usual target of our verification. Why this is the usual kind of target? Because we can do what John was asking. Here we can write a predicate that say this list is sorted by using logic formulas, and then we can try to verify them. Okay? So we base our verification a lot over this. Now, why this is good for us? So I think the one that is the main point is this one, which often is not what people that come from the theory background think about. So usually you are, for the theory background people, you are more used to try to reduce a problem to another in a specific way that you can solve maybe the constraint using a linear arithmetic and you're done. For us, instead, we are trying to have a kind of a very general way to encode constraint, because we want to consider all the possible programs, and we want to consider very complex pre- and post-condition. So we don't want to reduce to linear constraint. We want to have as much as possible and rely to the solver, the effort of trying to verify them. So the other reason is SMT solvers are good at handling a combination of inductive theories and numeric theories. For instance, if you want to work with arrays, you have a theory of array that you can use directly in the solver. And also, in theory, they could support counting theories like the one that we need to reason about probabilities. But the problem, actually, they can support theory like counting theories, but the problem is unclear how to make them scale in practice. Okay. All right. Any question on this? Then I go back to our goal. So because we use this SMT solver, and as I say, they could reason about probabilities, but it's not clear how to make them efficient and scale to big. Imagine probability distribution with a very big support. Then we want to avoid as much as possible reasoning about probabilities. For this reason, we my collaborator and I, but also people before, look at how to verify these relational properties and probabilistic relational property. And a technique that emerged is the following. We call it reasoning with approximate probabilistic coupling, and I will explain later why is this. But is the idea of just use some logical constraint as a postcondition, and require also some additional property. In the case of differential privacy, we want to ask that we pay the most epsilon. So this seems maybe like natural, because it's what we did also for pink, but in some sense is a non-trivial change, because we need to guarantee that this is a sound way of characterizing differential privacy. And I will talk a bit more about this later. Okay, since to simplify, I will just consider one program, but I will use these indices 1 and 2 to talk about the two possible run, the database 1 and database 2 and so on. Okay, so how do we verify our example? So our precondition now is that B1 and B2 differ in one individual data. Just as a shorthand, I will write it in this way. So I will write B1 squiggle 1 B2. Okay. Now, I I had slides for doing this example completely, but then I realized I'm running out of time. So let's say that by some standard reasoning, like the one I showed you before in the example of add, we can do the non-probabilistic part, okay? In particular, in this example, what will happen is that the adjacency relation we have on the data set will be propagated on the counting. We are counting with CDF, and so it will be just propagated this adjacency relation to the counting. So now the interesting part is what we do with Laplace, because now we have probabilities. So what can we say about Laplace? And here is where we use this first rule that say that if I have two inputs which are adjacent, and I add Laplace with epsilon, parameter epsilon, then I can say that the output are equal by paying epsilon.
You really mean like 1 over epsilon? Like this is not to be taken as the variance of the Laplace, it's just
yeah.
a parameter to a function.
I agree, but usually we use Laplace as Laplace of 1 over.
Sure, yeah.
Okay, yes. That's good, yes. It depends on how you implement the Laplace implementation. Okay, but I agree. All right? So now, remember I said before, when we introduce a rule, we need to prove them sound in the semantics. Now, it's in the semantics that we use this approximate coupling I mentioned before, and I will come back to that. But for the rule, mainly is this rule that we get, okay? Just say, mainly, by paying epsilon, we cannot distinguish anymore the output. Now, by applying this rule, we get that the output cannot be distinguished, and so we are done. We proved this differentially private because that was our goal. So our goal, just to make sure, going back here, it was exactly to prove this equivalence and paying at most epsilon. And we did this. Okay? Now, I will skip a bit on how these account for multiple queries, and I can do composition, and I can sum the epsilon and so on, because it's in spirit similar to what we saw so far with Pink, Rabat, and Fuzz. And I will try to focus on something a bit different. Also because last time I showed that part, Thomas told me, oh, but this is all trivial, so I want to show something that is non-trivial. It was some years ago, and actually this comment motivated what I will present next.
You're still sore.
All right, so as I said, we can extend with composition and so on, but let's look at something that doesn't use composition. So let's look at report noisy max. For the one that are not familiar, so here we want, let's say we have some item, and we have some scoring function for each item, and we want to report the one that maximizes this score. Okay? One way to do this is, for instance, by computing an histogram, adding Laplace, and then take the element that has the maximal score. Now, if I learn not to click, okay, at least one for each presentation, I'm allowed to do that. So now, if we just do a naive analysis of this algorithm, since we do a naive analysis with composition, we can show that this is k epsilon differentially private, but this is not the interest of this algorithm. What we want to do is instead prove this algorithm epsilon differentially private. And why this is epsilon differentially private? The idea is that mainly we look at two databases, we look at a bunch of queries, we add the noise to each one of them, and then I assume that they are one sensitive, and then we are looking at something like this, where the green part comes from database D prime and the blue part from database D. And it is true that if we look at the realization, maybe we can have that the max that is max in one will not happen in the other. But if we look overall and we try to coordinate the noise, we can show that mainly we are allowed to pay just for the max result. Now, this is a very high level intuition. Maybe other people have different intuition, but let's try to prove it formally. Okay, now I will not prove exactly report noisy max, but I will prove what is called the report one-sided noisy max. So this is slightly different. The main difference is that instead of using Laplace, here we use the positive Laplace. Okay? So one-sided Laplace. Why? Yeah, or an exponential distribution. Yeah, sorry. Now, why do we do this? First, because composition here doesn't apply at all, because one Laplace is even not differentially private, so we cannot apply composition. Second is that this gives an implementation of the exponential mechanism. So at the end of the day, what we will have prove is that an implementation of the exponential mechanism done through this report noisy max is differentially private. Okay. Now, let me try to go quickly through the code. So this function takes k queries, takes the data and an epsilon, and return one index. In particular, what it does, it goes through the queries. It adds to each query this exponential noise or this one-sided Laplace, and then try to just find the maximal one and keep that maximal one, and then return the maximal. Okay? We use a bit of variables. In particular, we use the current result, and we check the current result against the best result we saw so far. And if this is the case, we say that the index of the query we are looking at is the max, and we update the best to the current. Now, there is only one thing that is a bit strange here, this I equal to 1 that we use for the first step. Adam, you have a...
I guess I was wondering if it changes anything or makes it easier or harder if you just sort of consider two separate things, one where you add noise to all the scores and then
go through.
You're sort of doing two things in one while loop,
yeah.
Which if undergraduate students or anything to go by makes the program harder to reason about.
Mm-hmm. That's true. So I think that concretely nothing changed. You need to use the same kind of reasoning, but is the modularization of how you structure the proof that change a bit.
Okay.
Yeah, there is a lot of work that we can do in that direction. Now, what strategy shall we use? So here we use something that people use a lot on pen and paper. But for us, we need to make it explicit. And this definition of pointwise differential privacy, or this reformulation of pointwise differential privacy. If you, so I assume that the output domain is discrete. Then what we can do is to look at the indistinguishability on one particular element of the output domain, and then check that the delta sum up. In our case, we don't use delta. In this setting, I don't use delta. We just use epsilon, but we can deal also with delta. But the key point is that we can focus on one S at the time. Now, why this is interesting? Because if we turn this into a rule, and we remember that what the strategy we use to prove is symbolic, so we don't go brute force, what we can do is we can generalize over S, and so S becomes just one possible output. Is what you do on paper. You don't really take S1, S2, S3, but you take an arbitrary S. It's the way natural proof on pen and paper go. But now we can internalize this also in our proof, so we can say that if for every S we are able to show that we pay something, and we have this postcondition that say if the first output is equal to S, then also the second output is equal to S, then we can prove the overall program differentially private. Now there is this postcondition is a detail. I'm happy to explain why it has exactly this shape if you want later. But the key point here, and also don't focus on the delta, the key point here for us is really the generalization so that we can say we look at 1S in general. Which in which in our setting allow us really to just focus on a particular S. So we have this variable S now that we can use, and that this will be our specific output.
Sorry, can you go back?
Yeah.
This is the place. Okay. Maybe one more slide. I'm not sure where I got. Can you explain the first postcondition? So it says if under both inputs you would get output S, and you paid
epsilon and delta S, which is specific to S. And if I...
Maybe this exposes like something I was confused about, what it means to the statement paid epsilon delta, like what that actually means. In particular, what does that mean in conjunction with like a
this one.
Condition like
yeah,
that one?
I will come back later. That's exactly the coupling. The reason why we call this coupling. So we pay to get different couplings. That's the idea. But I will come back, if you let me go through the verification, I will come back to this after.
So paying for now needs to be understood as kind of how much you need to move in some metric space in order to...
Okay, I see it. So let me go back here.
Speaking of semantics, what are the semantics?
So here we are saying, sorry, this should have been adjacent. Yeah. So if I'm adjacent and I arrive here, this means that I cannot distinguish anymore the two outputs because they are equal. But to arrive there, I had to pay epsilon and delta. That's why I tried to put the past sense.
No, but what does pay mean?
It means that, so in your privacy budget, in the usual way, you have to consume epsilon and delta to do the...
I think we're asking, like, what are the semantics of the statement pay at epsilon delta? So is it a statement of the form, you know, I've got these two, I'm tracking two distributions, and it's like a coupling statement that says there exists a coupling of these two probability distributions under which they are equal with probability 1, and the
let me go to the definition so that we have the exact semantics. So and then I will go back if needed. So what we call approximate coupling is so coupling usually is used to put two distributions on the same space. And here we do two modifications. One is we have an explicit relation between that make the coupling explicit. And the other is we do this approximation. But let me go to which is usually a divergence. But let me go to this. This is the definition, and unfortunately is a bit long, but let me try to read you through it. So now we have two distributions, mu1 and mu2, and we say that we have an approximate coupling where the approximate is for epsilon delta, and for the formula S, is this a relation. So mu1 and mu2 are two distributions, and we have a coupling in our sense. If we can see two probability distribution on the joint space, and here we are a bit different from the usual coupling, because usually you want one probability distribution on the joint space. Here we take two of them, and the reason is because we also handle subdistribution, and so these two are sometimes needed. So, and we want that the left margin of mu L is mu1, the right margin of mu R is mu2. This is similar to standard coupling. And now, one of the key points is that the support of this coupling is in this relation S. Okay. And then we require mainly that that these two are epsilon indistinguishable, these two distributions, epsilon delta indistinguishable. Okay, this is the precise semantics. Now, the way I was using paid is to say that to get this, I see this in this way, to get this relation S, you are paying in the sense that you are making them indistinguishable with respect to this relation S, epsilon and delta. Let me give you an example that is different. So we already saw an example. Let me go back. To the ruler here. So this is one. I was saying that if we start with two inputs that are adjacent and we add Laplace of 1 over epsilon, then we can show the equivalence relation by paying epsilon. So it means you look at the same value and they are epsilon indistinguishable.
So that's saying that mu L and mu R, like output 1 equals output 2 is a description of S in your coupling language?
Exactly. So mu1 and mu2 mainly are in the diagonal. Sorry, mu L and mu R are in the diagonal. The diagonal is where they are equal.
Right.
Okay.
And at the end of...
But this is not the only way. Let me show you another example, which is similar.
Wait, maybe that one was a good one.
Sorry, now I'm... All right.
I'm just going to stop looking.
1 second. Let me just mention this. So now you're not looking at the diagonal anymore, but you look at output 1 plus k and output equal to output 2. And what you pay, and this is the same program. Here I was doing this for the exponential, but we have a similar rule for Laplace. Now you pay k times epsilon. This is what you call a sliding property, for instance, in your smooth sensitivity paper.
I'm still parsing, sorry. So input 1 minus input 2 is somewhere between minus k and k prime minus k. And then...
Yeah, this is because we are looking at the one-sided, so it's a bit more tricky.
Yeah, I see. I think I understand what that says.
But if you think...
This is still like, I mean, this is almost like that statement about the diagonal, right? This is like, you know, you are using a different relation, but it's still one where like the two random variables are, there's like a one-on-one correspondence.
This is exactly the sliding property of Laplace.
So,
generalize to all the points.
Maybe a more interesting one is that one you showed us that you were going to use for report noisy max. That I think one before this, go before. Stop. No. Yeah, earlier. You had the one with output 1 equals s and output 2 equals
So,
s.
for instance, this is another. So if we take, and we use it a lot in the proof. So if you take, again, you add the Laplace, one-sided Laplace. Now, what you can do is to just use a coupling which is zero indistinguishable by requiring that the output preserve the distance over the input.
I see.
Okay. I mean, same distribution, same.
Yeah, which is sort of like saying adding the noise doesn't make things worse.
Yeah. Exactly.
And Marco, these rules do you prove within the system, or this is something?
No, so I will probably not show completely the example because I'm running out of time, but I think it's better to just discuss. So this rule can be proved inside the system, but not inside the logic. Let me be more specific. Usually this kind of logic are built in some system that allow us to reason about their soundness as well. And then you can use these rules as macro to do the proof like I was doing. So they are proof correct, but inside the bigger system, not the rule themselves. So just, I will not go through this, but just the key point of report noisy max, let me go here, is that we need to proceed by cases. So what we do is mainly to think about in this way. Now we are reasoning about S. So we can think about the loops before S. We can think about the case S, and then the loop after S. Since the output must be S, we know that we don't want to pay for the loop before and for the loop after. So we use this coupling that we just saw, the one that pays 0, in all the iteration before S and all the iteration after S. And then we use another coupling for the case where we are in S, which is this one. And this makes sure that, so we use this with k equal to 1, but mainly it makes sure that we can prove this postcondition for the result. So that if we take the branch, if we go through the if for the first run, we can force also the second run to go into the if. And then we keep paying 0 until the end. Okay. This is at high level the proof. And the detail are in my slides. Let me conclude by saying we have other coupling, this approximate coupling for other divergences and Rényi divergence and ZCDP and so on. It's not totally trivial to do this from the formal perspective. And there are also for F divergence more in general. This method can be automated, and Justin Shu work on this with House, and House will be here also during the first workshop, so it will give more detail about their way of automating this approach. And I think is very interesting. Another work I wanted to mention is that a very similar kind of verification can also be done for reasoning about probability of failure. And this allows us to reason about accuracy. For instance, for a poor noisy max, we can, with a similar proof, we can prove its accuracy as you would do paper and pen. What this logic internalizes is the union bound, mainly. Now, I take a few more minutes with some pointer that I think I would like. I think they would be interesting for some of the possible interaction in this semester. So I think the first, Adam already mentioned it, and I think is an interesting question, try to find a common way to try to build some software infrastructure that support different effort for differential privacy. But I will go fast on this because Adam already mentioned this several times. The other one is, I think it would be really great to have basic mechanism like, let's say, Laplace or exponential mechanisms that are fully verified end-to-end, in the sense of having some basic component maybe written in a low-level language like C, but which is something we are sure that is correct, maybe correct also against some of the low-level attack. And I personally plan to work on this, but I would like to hear more from other people about this and whether this is something interesting. Another topic that I think we should be discussed at this semester is finding counterexample to differential privacy implementation. So since differential privacy is being deployed by many different people, that sometimes they don't have the expertise that there is in this room, many of them are worried that their implementation are not private. So I think having some way of thinking about finding violation is a good way to help the deployment of differential privacy. Sorry, I did a bullet list, and another thing that I already discussed with several of you is we use a lot this coupling-based argument, and we also use a lot of divergences in our verification, and recently several work have shown lower bounds based on some kind of argument based on coupling, and the idea is usually in the proof that I saw, taking some divergence, maybe depending on the problem that you formulate the problem in terms of some divergence and try to show that by some transformation you have a bound on the divergence you need for differential privacy. Last one, I think formal methods doesn't need to be thought only about something for privacy in this semester, but there are also other directions that it can be useful for. For instance, John and I are working on some program analysis technique for more adaptive data analysis. House has worked a lot on fairness and formal methods, so I think it would be very interesting for me and for other formal methods people learn more about other possible applications. And with this, I'm done.
Marco, can you go back?
Yep.
I'll tell you when you get that. No. Which one was it? Go forward again. Sorry. Oh, right. My question was about how end-to-end can we, like, just what are the ends of verifying a basic mechanism end-to-end? Do you mean like on particular hardware?
So
in some model of what C is? I mean,
Yeah, so that's a good question. So different, so I think what I was referring to is some of the work that are going on in more the cryptographic world, where they are trying to verify some crypto primitive end-to-end. And usually the way, at least some of the work I have in mind, the way they do this is they prove some property of the high-level language, which is then translated to C, and then we use some infrastructure that is already built to reason about C programs, and these can go to assembly. So it can go to some architecture even, or to some intermediate architecture like LLVM or things of this kind. So I think the lowest we push the argument, and the better it is. Now, the effort, I think, which is needed is really reason a bit of two things. One is differential privacy on finite memories. Like Ilya did something, but it's not the final word. People at Harvard, Victor Balcher was working on this. He has some result. I think there is the need of thinking more about differential privacy in a finite space, finite memory. And then maybe there is a more formal method effort in trying to understand how to push down this requirement. But there is a lot of software, a lot of verification effort that has already been done. Like C, to give you an example, C has already been formalized, different memory model, different architecture, so there is a lot of work in that direction.
We thank Marco for all three.
Yeah.